Section 7.5 on page 672. With the last one we are going to do is conic sections. Now you have already, I'm sure you've already done conic sections in the past, right? That's the parabolas, the ellipse, which includes the circle, but we're not going to talk about the circle much. And lastly, the hyperbola. And so you have probably done it, but the book wants to review it and maybe go into a little more detail, so we're going to do that. And first, what is the parabola? But the parabola, as you remember, is the quadratic equation that, you know, the bow thing. And then, but we are going to define it in conic sections. We're going to define the parabola a slightly different way. The parabola is going to be called something like something that's equal distance from the focus to the directrix. So you have the parabola here, and what is the point on the parabola? See the pxy? It has to be equal distance from the point F called focus, and the line is perpendicular to the line directrix. Okay, those two distances, both marked D, has to be the same. Now, if it is the same, and then you crank out the entire equation that way, and once you have done that, that will give you the parabola. Now, to do that, to be exact, you will have, here's how it's done. Okay, if you don't remember it, this should be done in pre-calc or trigonometry or something. Anyway, what you're gonna do is set up the equation where the two distances are the same, square both sides, clean it up a little bit, and come out with a parabola equation right down there. See, neat and clean. That's because that parabola is on the y-axis or something. And then anyway, yeah, so let's look at the next page. So here's your equation of the parabola. Theorem, excuse me, 7.8, which states that a parabola has the general equation of y equal to 1 over 4p. P is some number that is something has to, what was p again? Is the focal point, okay? It has to do with the distance between the focal point and yeah, look at the p. See, p is the distance between the focal point and the vertex. Anyway, so the parabola is given as y equal to 1 over 4p, where if it's located, instead of at the origin or close to the origin, is located at h and k. Yeah, if h and k are 0, that would be the origin. So if you move the parabola somewhere else, then you stick the h and k in there. But generally speaking, that you got the parabola, and that is done in the past. So I'm not going to go too much into details here. However, what you didn't learn in the yeah, and I should also mention that the parabola, of course, can look different, right? It can point up, down, left, right, and the numbers are adjusted accordingly, but they're all the parabola. Generally speaking, a parabola will have a general form down here. See, you have let's see, you have such as where x is squared, the first one over here, or y is squared, the second one. The x squared is the one that goes up and down, while the y squared is probably the one that goes left and right. Yeah. Anyway, so please do example 7.19 as part of your homework, where you have general some parabola or quadratic equation. You need to figure out where it is. That's something that's done in the past. Nowadays, we just type. You can just type it into the Desmos calculator, and the parabola will pop right out. To type it into the calculator, you just need to get the normal, the average, or the general calculator. You don't need some special Desmos calculator. You just type in this entire thing. Okay, you start typing x squared blah 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 plus 12, and then type in equal to 0. Once you do that, the entire parabola will pop out magically. That calculator is awesome. Of course, you should, however, know how to do what the book wants you to do, which is to turn some general thing into the parabola form. You have to do something called completing the square. Now, if you don't remember how to do that, just look at this and you'll remember in a big hurry. And that's the end of the parabola. No, except one thing. The parabola, if you remember, has that specific quality that if you pretend that this is the flashlight, that is the parabola is the flashlight, the focus is where the light bulb is, and when light comes out of the focus, your light bulb, it'll hit the parabola wall and then shine straight up. That is how most flashlights are made. You have a parabolic surface, and then the light can be reflected straight out. And that's just in theory. In reality, the light doesn't reflect that straight, in my experience, but that's the theory. Okay, the theory is that the parabola will reflect your light right out. So please do example 7.19 as part of your homework. Next, let's look at the following page, 677, where we're looking at the ellipse. The definition of the ellipse is such that the distance from any point of the ellipse to the two focuses, okay, the distance is constant. In other words, look at the red line there. It goes up and down. And then that other color, what is that color? Let's call it green, okay, which goes up and down. Imagine the red line is a rope, okay, that's fastened at the two focuses. And you have a pen stuck at, say, point A, and you follow the rope or string, and you follow the string clear across. So that, and you can draw the entire ellipse that way. And that is, that's the distance. That is the distance is, that distance is the same, okay? If you keep drawing that way, you can you will be able to draw an ellipse by using the string method. Now, if the two focuses of an ellipse is identical in the same spot, then it becomes the circle, right? The circle has just one radius. The ellipse doesn't have a radius because the string got split up, and most of the time the string looks like a triangle, right? It goes up and is fastened on the two focuses. Okay, the ellipse has various names. There's the major axis. That's how wide it is from one end of the ellipse to another. The minor axis, that is the narrower part of the ellipse from the top to the bottom, and then maybe some other name. Now, before I forget, I want to show you the directrix of the ellipse, because I don't notice the book mentioning it until the definition, then they tossed it in. The directrix of the ellipse is, well, the directrix is, what is it called? I don't even know. We'll talk about that later when they define it. But here's the directrix of an ellipse. I found this picture online. It's some line on the outside, and it probably has a ratio of, the distance from the focus of a point to the directrix is constant or something. Yeah, I think, yeah, the eccentricity. We'll talk about that a little later. I just want to show you a picture of the directrix because the book didn't actually draw a picture of it. Probably forgot, but that's understandable because the directrix of ellipse is not mentioned much, that in my memory anyway, but you know what it is, okay? It's something like that. It's very similar to the directrix of the parabola. So then next, we are gonna calculate the, what is that? The formula, okay? Now the formula, like I said, that the formula of the ellipse is calculated by that string that I mentioned, okay? The distance, the sum of the distance of a point to the two focuses stays constant. And that's how you calculate the formula of the ellipse. And you have to derive it, of course. And what happens, the derivation is at the bottom of the page. See, what you do is you end up, the distance is the same. What is the distance? The distance is just the length of the major axis. That is 2a, because a is half of it, half of the major axis. And I should probably mention that. Yeah, see, look at the picture carefully. See, the entire width, or the widest part of the ellipse is 2a. See that 2a there? And the entire height of the ellipse is 2b. And those are the numbers. And then the focal point is located as something to do with C. That is, the focal point is located at C and minus C. So when you do that, then the equation of the ellipse end up being two distance formulas, and you have to derive it. So what you do is you have two square roots, right? And then you have two square roots And what are you going to do with the 2 square roots? You're going to isolate the square root on one side, right? And then you're going to square both sides, which will get rid of 1 square root. Then you toss everything to the other side and square both sides again, or something. Well, you clean it up a little bit. And then that gives you, that eventually come up with a polished stuff and give you a fairly clean formula after you clean everything up. This part was done in when you learned this before, so I will have you do this part, deriving the ellipse formula, as part of your homework. It looks a bit tedious, but yeah, please do that. I think it comes out pretty readily though, even though there's quite a bit of writing. So please derive the formula of the ellipse as part of your homework. So let's look at the bottom of the page, theorem 7.9, where once you have gone through the parallel algebra and got to the equation of the ellipse, where eventually you're going to apply the equation where a squared minus c squared up here, see the a squared minus c squared, is equal to b squared. That's important, all right? And also, I think on this page there's a slight mistake. On page 678, where are we right now? Yep, this is the page. I have a notes that says that it should say that c squared plus b squared equals to a squared. That's just a small typo somewhere. I don't even know where I got that. Whatever. I think maybe this part. This part is, let me expand this thing. That is this part of your book right here. I think this should read c squared plus b squared equal to a squared, okay? And that would be the correct answer. That couldn't, or something, yeah. Because these two equations can't both be true, right? I mean, look at this. If a squared plus, yeah, if that is true, there's no way this is true, because yeah, I mean the subtraction is just off. So it's pretty obvious why there's a slight mistake there, and you can fix that yourself. And anyway, so we have come down to, that's the general equation, where for ellipses, then there's that the b squared, this one is correct. Oh, the b squared equal to a squared minus c squared, and that gives you this equation right here. All right, now let's look at this more carefully. So here's the equation. Yeah, a squared minus c squared on top, okay, equals to b squared on the bottom. And then that gives us the theorem, which gives the standard equation. That is the one we derived before is based at origin. Now if we move it over to some spot called h and k somewhere, then here's the new equation, which is yeah, it is the same thing. The only thing we should mention is that the equation of the directrix is given at the bottom of the theorem. The equation of the directrix, as it says here, is k plus or minus a squared over c, and we'll just take it as that, okay, without saying too much, because we don't do the directrix of the ellipse that much, I don't think. In fact, I don't even think we did it once in the homework. Whatever, but you know it's there if you ever needed it. Anyway, so what is that? Okay, so next, let's look at example 7.20, where you have to calculate some standard form of an ellipse. And what you're going to do, you're going to complete the square, of course. So please do example 7.20 as part of your homework. Now, if you say, I have never actually done conic sections, or if you think, I've done it, but I don't remember any of it, well, that's fine. It's just, there's no calculus in here. It's just algebra. You know, you just look at it, and then the algebra is a bit tedious and long with lots of symbols and ABCs in there, but just follow the plan and you'll get it out. It's no big deal. And anyway, so next page 680, let's look at the ellipses, okay? Something about the sun is, the Earth's orbit is an ellipse. It usually is, because very rarely is orbit perfect circles. So it's some kind of ellipse, and then the ellipse has an interesting quality that is called whispering gallery, which means that if you stand at one of the focal point of the ellipse, a building that's elliptical, okay, and there are buildings like that, So if you stand at one point of the elliptical building on the focus, then you talk, and the reflection is such that if somebody standing at the other focus can hear what you say, that sort of thing. Yeah, and you will be doing a little bit of that in the homework. So let's move on to the hyperbolas. The hyperbolas are very similar to the ellipses, except that they're basically ellipses turned inside out. Okay, so then the hyperbolas go this way. You have for one standard hyperbola would be xy equal to 1, because except that that's sideways. This is straight. This is a hyperbola laying that's not tilted. Anyways, the point is, here's a hyperbola, and there are various names for it. Hyperbolas has asymptotes, as you might remember, and they have the major axis. And what is the major axis called? Transverse axis, and the vertical axis is called conjugate axis. Well, whatever. I never remember those things. So it has two vertices, and yeah. Anyway, there's a different definition of A, B, and C, where in this case C is bigger than A. Well, the definition of the hyperbola is different from ellipse in the sense that ellipse, as I mentioned, is the sum of a point distance to the two focuses, and then but the hyperbola is the difference of the distance between the two focuses is constant. But other than that, you will do the same math. You don't have to do it really, because if you've already done the ellipses, equate the hyperbola works exactly the same, except that so you have two square roots to do, okay, and then you have to square it once and then square it again to get rid of both radical signs, and then you clean up something, and then if you don't make a mistake in there somewhere, eventually you end up with the equation of the ellipse. The hyperbola, which is very similar to the ellipse. See on the following page, very similar to the ellipse, except there's a subtraction sign there, and and that is your hyperbola. All right. So I guess I'm not gonna have you do this as homework, because doing it once is enough. Let's not wear ourselves out here. So so next, in general, if your hyperbola is not located at the origin, then it's located at some other point hk, but the formula doesn't really change that much. The equation of the directrix is also almost identical to the one in ellipses. I don't remember if, yeah. Anyway, and then if the hyperbola is turned the other way, a vertical one where it opens up and down, then things are changed a little bit. But generally speaking, the hyperbola has a different situation that I should mention, where c squared is equal to a squared plus b squared, right here. See, then, and whereas, now at this point, things can get slightly confusing, and so I wrote it down in your notes below the video. That is for ellipses, c squared equals to a squared minus b squared. For hyperbola, c squared equals to a squared plus b squared. You just have to keep track of that. Maybe write that down somewhere so that all this information don't get confused. There's nothing really particularly challenging about the conic sections, except there's a lot of information, and some of the information can be confusing because, is it plus, minus, that. But as long as you keep careful track of it and write notes on which is what, then you should do just fine. All right, and because other than that, it's just algebra. There's nothing calculus about this stuff. Okay, so having done that, please do example 7.21, which is finding the standard form of some hyperbola, which I believe you're going to complete the score again. Next, let's look at page 685, the eccentricity, which you may or may not have learned in the previous conic section lesson of yours. But that doesn't matter. The eccentricity is the ratio of the distance from some point to the focus divided by the perpendicular distance from that point to the directrix. Now, it has an interesting quality if the eccentricity, called E, If e equals to 1, it is a parabola. If e is less than 1, it is a ellipse. And if e is bigger than 1, it is a hyperbola. Now those two distances sound very confusing, right? But let's just go here, okay? Now if you do a bunch of algebra, let's just say, well, simple algebra, and figure out what e is, this is what you're going to come up with. At the end of the day, e is equal to c over a for both ellipse and hyperbola. And I have also that written down under your video, in your video description. This is, you remember that e equal to c over a, okay, in both cases. And you don't need to worry about the parabola, because parabola e is just 1. So then saying e equal to c over a is important for you to note, because you're going to need that to do your homework. Okay, I mean, instead of whatever is said, distance between focus to let's not imagine that. So where c over a is much better. Okay, so just remember e equal to c over a in both, for both ellipse or hyperbola. Doesn't make any difference. E is c over a. And then in your homework, they'll tell you what is the e is and what is a, and then calculate the formula or something, and then you can totally crank it out. All right, and that's what you're going to be doing. Now, next page. What's that? Okay, example 7.22. Determine the eccentricity. Yeah, go ahead. What is e? Well, e equals c over a. So figure out what c and a is, and then you'll be able to crank it out. So please do example 7.22. Now next, we are going to do the polar equation of conic sections. Now, when I was doing this stuff, preparing this part of the homework, there turns out to be a mistake in here. As a result, what I did is I was calculating the orbit of a planet, and my result was that the orbit of the planet will fit in the palm of my hand, which totally freaked me out. I thought I went off the deep end, but eventually I realized that there was just a slight mistake in the formulas here, which is why I messed up. Now, I'm not going to tell you where the mistake is. I'm going to let you do the homework, and then you can also calculate that the orbit of, I don't know, Mars or something is actually will fit in your hand, and then you can figure out where the mistake is. But I will mention what the mistake is at the end of the homework section. So I will tell you, but not right now, because I want you to experience the same fun thing I did. So once I did that, I told my family that I calculated the orbit of some planet to be fit here. So everybody laughed, and it was so funny, right? And so we all had a great time. So I'll let you enjoy the same fun, and then so we'll look at what is this talking about? Okay, the focal parameter. The focal parameter is distance from a focus to the nearest directrix. Okay, which is called P. Well, whatever. The point is, we have a chart, or P is, for the ellipse, for the parabola, P is just equal to 2a. For the ellipse, P is a squared minus c squared over c. For the hyperbola, you flip it around, is c squared minus a squared over c. And the point of the focal parameter is the formula at the bottom, which will give you the, what is this? The polar equation, okay? That is the equation of some of the conic section you're looking at in polar form, something like this. That is, when you need to calculate the polar equation, you figure out what E and P is, right? And plug it in here, and there it goes. It says something about plus and minus. That's because, well, try plotting both on the decimal graphics calculator and see what the difference is. Well, the way they both work, that's why there's a plus or minus here. And I've tried it, and all the difference is your conic section, like your ellipse or something, it just moved over a little bit. That's it. That's the difference between the plus cosine or plus or minus the cosine, etc. So that's the equation. Your book didn't show how they come up with the equation, so I'm going to skip it too. Let's move along, and then graph some conic section that is in the polar equation. We have, so that's the next example where they got you some points to expect you to graph it by hand. Let's just type it in some graphics calculator and call it done. All right, let's not do it by hand. what are we doing? So please graph example 7.23 as part of your homework. Next, let's go to page 688, the general equation of conic sections. Generally, the conic section can be written like this, where the big ABCs, D, E, F, those are all numbers, whereas x squared, y squared, xy, etc., those are the variables. Now, if you have a term that's xy, where number b is not 0, that means your conic section got turned. Okay, the most famous one, or the easiest one, of course, is xy equal to 1. Now, if xy equal to 1, see down here, then means y equal to 1 over x. And you remember what that graph looks like. That's just a basic hyperbola. So, but in general, however, there's something called discriminant, which is 4ac minus b squared. That thing is called discriminant. Okay, now 4ac minus b squared, if it's bigger than 0, it's an ellipse. If it's equal to 0, it's a parabola. And if it's less than 0, it's a hyperbola. Now the book is not going to prove that to you, so I'm not either. Let's move on. Yeah, and then you even have a rotation trick. That is, if you have something that's tilted, like xy equal to 1, okay, which is a hyperbola, right? But it's tilted. It's not straight up. It's like sideways. Now, there's a way to turn it so that it doesn't, instead of sideways, it'll sit straight up like it's, or straight level or something like it's supposed to. And there are a bunch of formulas to do that. If you follow these formulas, this is all the formulas, okay? This is what angle to turn it at. That's what theta is. So if you calculate the new a prime, which is take the old a and do all that stuff, the angle you're turning, then you crank out a new equation after you've gone through all that work, and you come up with some new equation, then your parabola or hyperbola or something will no longer be in the wrong, slanted. It'll be straight up or straight down or something like that. So, so that is what we're doing, and which sounds like a lot of work, and it is. So I'll let you do that, which is example 7.24. Please do that as part of your homework. And of course, the opposite is true. That is, if you have a perfectly straight up ellipse or something, and you want to turn it at a specific angle, then you apply that formula or something. Maybe apply it the other way. I don't know. Anyway, there's that formula that helps you turn the thing. Okay, let's turn it if you need to. But it's well, anyway, that should be good enough for the end of the, yeah. So now we have come to the end of the section. Let's do homework. The homework you need to do is problems. Okay, the homework is on page 692. Please do problems 259. 265. I guess there is a small error there. It should read minor axis or something. I'm sure you will see it when you see it. Anyway, what is that? Did I say 269? I mean 265, then 269, 71, 73, 75, 77, 79, 81, 83, 85, 87, 299, 301, 7, 13, 17, 19, and 21. And then that sounds like quite a number of problems, but they're all pretty short. They're not, most of them are not near as hard as the examples that you had to do. But the examples are important because they give you a feel of the conic sections, in case you don't have a feel for it. After you do that stuff, you totally get a feel for it and feel like an expert. So please do your homework, and when you come back, I want to talk about some of the problems. Okay, now that you're done with the homework, let's talk about some of the problems. First, problem 259. Parabola, very straightforward. You just, the information is given to you, so go to the definition or something and plug all the proper numbers right, and here's the answer I got, which is correct. Now the book wrote it differently. They isolated x squared, which is fine. I don't know why. Normally we say y equals something, not x squared equals something. But if the book wants to do that, I'm fine with that, okay? Now next, problem 265. The only problem is it says major axis. It should say minor axis, because otherwise the problem doesn't make any sense. So other than that, everything comes out, right? You draw your ellipse. and then figure out what C is, C and B, and then figure out what A is. And remember that formula where A is, well, whatever. Like where A is that, okay? And then plug it in, and there's your answer. Next, problem 269, which is, this is slightly different because this one gives you the eccentricity. Well, you just remember the eccentricity. What is it? Eccentricity is C over A. And with that, you can calculate what all the other stuff need to be. A is 4, I guess, and B is that thing, which is square root of 2, and then you just plug it in here. And that is your answer. That's 269. And finally, 271, the hyperbola. Yeah, same idea. You figure out what C, A, and B are from all that information, okay? There's various information. Some is slightly confusing. You just have to focus and pay attention to what is A, what is B, what is C, and then write it down. See, it's very short. The answer comes out right away. All right, next let's look at problem 273. Straightforward problem. We have B equal to 3, C equal to 4. Therefore, A equal to do some equation, and then you plug it right in. There's your answer. Next, 275. Same thing. You figure out what A and C is, and then it's just in a different spot. So you move it to that spot. New center is somewhat off. Plug it in, and there's your answer. Next, 277. Yeah, another problem, except that now you have the eccentricity. Well, remember, eccentricity is C over A, always. So therefore, knowing that, then you can figure out something, and then yeah, well, I don't even remember which one you're figuring out. Doesn't matter. You'll figure something out, and there's the answer, okay? One step. 279 is a parabola. E is equal to 1. I guess that's all there is to it. Next, 281, we're just writing down the equation, I think. The equation is, the equation has to be 1, okay? It has to be, on the bottom has to be 1 plus something. So you divide you start out at 2, so you divide by 2. Then you get 1, and then the eccentricity becomes 1/2 right here, which makes this equation an ellipse. The next one, the eccentricity is 3, which is bigger than 1, so make this equation a hyperbola. Next, 285, we have P equals to 4. What are we doing here? Well, whatever. The point is, we come up with something. The x equal to 4 is vertical, so the major axis is horizontal, I guess. Anyway, the answer, therefore, is cosine. Yeah, the reason is very simple. I don't remember what it is, but I'm sure it's just a one-step thing. Same thing at 287, where y equal to 2, the major axis is horizontal, therefore your answer has to be in sine. I have plus and minus here, but the answer in the back of the book just says plus, and that's good enough for anybody, okay? The minus one just moved it a little bit. It doesn't really make that much difference. So you can just write down the plus answer, and that is good enough. And then next, problem 299, I guess that's the answer. I don't know. And 301, that's what? That is a ellipse. And 301 is a hyperbola, I suppose. That's all I wrote down, so that must be good enough. Next, problem 307. We are going to look at the discriminant, which you plug into that 4ac minus b squared, which come out to be something that's less than 0. You don't even care what it is. The point is then it's a hyperbola. I hope I got, yeah, it's a hyperbola, and that's your answer. I mean, it's negative, so you don't even care what it is. The point is less than 0. 313, we have something, I don't know, there's a p, and you calculate what a is or something, and then what y is, and there's your equation. And then you end up with the answer, p is equal to 2.25 feet. P is the focal parameter. That's the distance to the focal point that you need to put whatever that thing is, that you need to put it there so that everything comes out properly. Anyway, next 317, we have that interesting dome, okay, where you can whisper and then the other guy can hear you. Now the question they ask you is how tall is this thing? The reason it asks how tall is because the top part is a ellipse, part of the ellipse, and well, this is, which is, well, anyway, in the past, I've only done the walls to be an ellipse. This is the first time I see something where the top is an ellipse. And in fact, the Grand Central Station is built that way. Okay, you can't, where the roof is an ellipse, so they can stand somewhere and whisper, and somebody else, across the room can hear you just fine. So that is, but anyway, that's the problem 317. Well, you do the same as you always do, right? You figure out what B is or something and what C is, and then crank it up. And then, well, yeah, the question is what is B? Then you calculate that B is that number. And that's problem 317. Where's the next one? Okay, next, let's look at problem 319. And that is where I got the mistake. We're supposed to calculate the, I don't know, the orbit of something, some object. And then I calculated it to be less than the palm of my hand because I followed this formula. Now, if you didn't follow this formula, you see there are two formulas for P, right? Now, I follow the second one over here. And if you follow the first one, you would have been just fine. But I follow the second one because there's an E in there. And what I didn't notice is that A is missing a squared, okay? There's a squared here for A. And if you're missing that squared, then I'm missing by the major axis of the orbit of some planet or something, which is why I was way off. So that is, I'm missing by how much? I'm missing by more than a mile, okay? I'm missing by a zillion, well, yeah. Anyway, I'm missing by a ton. What am I talking about? Where's my problem? Anyway, so once I found the mistake and then punched in the right number, then everything turns out just fine. So that is my equation. After I found out that there's an A there, okay? Imagine doing this equation for the orbit of some planet or something, and you don't have A in there. You just have the rest of it, which doesn't make sense at all. And then, yeah, and then it comes up. One thing I want to mention is the answer in the book is slightly off from what I have. The answer in the book says 2.62. I mean, it's 2.61, and I come up with 2.62, etc. with two different calculators. And I think the reason the book is slightly different is because the book might have used only part of the decimal representation, whereas I used all of it because I typed this entire thing, okay, into the numerator. 1/2 times, etc. The whole thing typed in, and it came out with the answer instead of doing part of it and then retype the number in with truncated decimal points. And it's important that you keep all the decimal points when you do this kind of a apply problem. That way you're precise. And I'm positive the book is off in that decimal point because I typed it into used two different calculators, and I came up with the same answer. But that's not all. And because of that, I also did the next problem, which are identical. Okay, here's some other planet or something has a slightly different orbit and information. I come up with this, and this is I got it exactly the same as the book. So being that these two are identical formulas, so I'm positive the book is off by a little bit on the second decimal point. There should be 2 instead of 1. So with that, that's about it. And that marks the end of this section, and in fact, the end of Calculus 2. So, at the end of the Calculus 2, I would recommend that if you're finished with this, to go on to Calculus 3. Because as far as I remember, I haven't looked at it, but Calculus 3 is no harder than Calculus 2. It's just, it's the same stuff. In fact, this book put differential equations, at least part of it, in Calculus 2, which I did not do that before. So that is differential equations considered normally is considered a tough part of calculus 3, and you've already finished it, which means you should not have any trouble doing calculus 3. So if you're at this point of the book, at this point of this class, I highly recommend that you go on to calculus 3, which is have a bunch of stuff. There's still a bunch of calculus that we haven't covered, and they're all super exciting. So hope to see you in calculus 3.